everyone, and welcome back to the channel. Today, we're going to talk about something we see almost every single day, something that's so familiar we often take it for granted. I'm talking about that giant, glowing ball in the sky, our sun. But how much do we really know about it? Let's go on a journey 93 million miles away to properly meet our star. First things first, the sun is absolutely massive. It's so big that you could fit about 1.3 million Earths inside of it. Imagine that! It accounts for over 99.8% of the total mass of our entire solar system. Everything else, all the planets, moons, asteroids, and comets, is just the leftover cosmic dust. The sun's immense gravity is what holds our solar system together, keeping Earth and all the other planets in their orbits, like a cosmic dance choreographed by this celestial giant. Without the sun's gravitational pull, Earth would just be a rogue planet, drifting aimlessly through the cold, dark emptiness of space. So what exactly is the sun? It's a star, specifically a yellow dwarf star. And like all stars, it's a gigantic, fiery ball of hot gas, mostly hydrogen and helium. The intense pressure and temperature at its core are so extreme that something incredible happens: nuclear fusion. This is the sun's engine. In the core, hydrogen atoms are smashed together under immense force to form helium. This process releases a mind-boggling amount of energy. Every second, the sun converts about 600 million tons of hydrogen into helium. This fusion reaction is what produces all the light and heat that radiates outwards, travels across the vastness of space, and reaches us here on Earth. That sunlight you feel on your skin? It's the product of a nuclear reaction happening millions of miles away. Let's take a tour of the sun, layer by layer, from the inside out. At the very center is the core. It's the hottest part of the sun, with temperatures reaching an unbelievable 27 million degrees Fahrenheit, or 15 million degrees Celsius. The pressure here is over 250 billion times that of Earth's atmosphere. This is the powerhouse where nuclear fusion takes place. The energy created in the core doesn't just shoot straight out. It begins a very long and slow journey. Surrounding the core is the radiative zone. The energy from the core, in the form of photons or light particles, travels through this dense layer. But it's not a straight path. A photon will be absorbed and re-emitted by particles countless times, zigzagging its way through this zone. It's like trying to get through an incredibly crowded room. This journey can take a photon hundreds of thousands of years to complete. That's right. The sunlight that reached you today might have been created before human civilization even began. Once the energy finally makes it through the radiative zone, it reaches the convective zone. Here, things start moving more dramatically. Hot plasma rises, cools as it gets to the surface, and then sinks back down, just like boiling water in a pot. This constant churning motion, called convection, is much faster at transporting energy. It creates these huge circulation cells, carrying the heat to the surface of the sun. And that brings us to the visible surface of the sun, the part we actually see. It's called the photosphere. This is where the sunlight we see is finally emitted into space. The photosphere isn't a solid surface, but a layer of gas about 300 miles thick. Its temperature is around 10,000 degrees Fahrenheit, or 5,500 degrees Celsius. If you look at the photosphere with a special solar telescope, you'll notice it has a grainy texture. These granules are the tops of the convection cells from the zone below, each one about the size of Texas. You might have heard of sunspots. These are darker, cooler areas on the photosphere. Cooler is a relative term, of course. They're still incredibly hot, around 6,500 degrees Fahrenheit, but they appear dark because they're cooler than the surrounding area. Sunspots are caused by intense magnetic activity that temporarily inhibits convection, creating a cooler patch on the surface. These spots come and go in a cycle that lasts about 11 years, known as the solar cycle. During the peak of this cycle, or the solar maximum, we see a lot more sunspots, solar flares, and other solar activity. Above the photosphere is the sun's atmosphere, which has two main parts. The first layer is the chromosphere. It's a reddish layer of gas that's only visible during a total solar eclipse, appearing as a red ring around the moon. Here, the temperature actually starts to rise again, which is a bit of a mystery to scientists. And finally, we have the outermost layer of the sun's atmosphere, the corona. This is a stunning, pearly white crown of plasma that stretches millions of miles into space. Like the chromosphere, it's also only visible to the naked eye during a total solar eclipse. The corona is shockingly hot, reaching temperatures of millions of degrees, far hotter than the surface of the sun itself. Why the corona is so much hotter than the surface is one of the biggest unsolved mysteries in astrophysics, known as the coronal heating problem. From this superheated corona, the sun constantly spews out a stream of charged particles called the solar wind. This wind travels throughout the solar system at speeds of up to 1,000,000 miles per hour. When the solar wind interacts with Earth's magnetic field, it creates the beautiful aurora borealis and aurora australis, the northern and southern lights. But this solar weather can also be disruptive. Strong solar flares and coronal mass ejections can send huge bursts of energy and particles toward Earth, potentially damaging satellites, disrupting communication systems, and even causing power outages. That's why scientists are constantly monitoring the sun's activity. The sun is crucial for life on Earth. It provides the light and warmth we need to survive. Plants use sunlight for photosynthesis, which is the foundation of almost every food chain on our planet. The sun drives our climate and weather patterns. Without it, Earth would be a frozen, lifeless rock. But our sun won't last forever. It's about 4.6 billion years old, roughly middle-aged for a star of its type. It has enough hydrogen fuel in its core to keep burning for another 5 billion years or so. But what happens then? When the sun runs out of hydrogen in its core, it will begin to fuse helium and other elements. This will cause it to swell up dramatically, becoming a red giant. It will grow so large that it will engulf Mercury, Venus, and possibly even Earth. Our planet will be vaporized. After this phase, the sun's outer layers will drift away, creating a beautiful, glowing shell of gas called a planetary nebula. All that will be left at the center will be the sun's hot, dense core, a white dwarf. This white dwarf will be about the size of Earth but incredibly dense. It will no longer produce energy through fusion and will slowly cool down over trillions of years, eventually becoming a cold, dark black dwarf. It's a dramatic end, but thankfully, it's billions of years in the future. For now, we can continue to enjoy the life-giving energy of our incredible star. It's a dynamic, powerful, and utterly essential part of our existence. The next time you step outside and feel the warmth of the sun on your face, take a moment to appreciate this magnificent nuclear furnace. You're feeling the energy from a star that has traveled 93 million miles just to get to you. Thank you so much for joining me on this journey to meet our sun. If you found this fascinating, please give this video a thumbs up and subscribe to the channel for more explorations of our amazing universe. And hit that notification bell so you don't miss our next adventure. See you next time.